Hi, I am Abdul.
I'm Rahul.
And I'm Michael, and we are the Bluetooth bicycle sensor team. In this video, we will give an overview of the final product produced in the project with a demonstration of the system, describe the evolution of the design since the beginning of the project, and we'll discuss some of the team's achievements and finally list several of the lessons we learned over the course of developing the module.
The Bluetooth bicycle sensor is a device intended for casual cyclists interested in seeing live statistics as they ride. Seeing speed, RPM, distance traveled measurements allow cyclists to pace themselves on their ride and to keep them close in their to their goals.
So the module mounts to common street bicycles and pairs with a smartphone using an Android application. The sensor used is a reed switch, which is mounted on the bike frame near the spokes of the rear wheel. A magnet is mounted on one of the spokes so that it can trigger the sensor, and then each time the magnet passes by the reed switch, this is sensed as 1 revolution, which is then sent to the central module, which contains a Bluetooth low energy microcontroller. So this microcontroller sends a signal to the paired smartphone, which then uses the time since the last trigger and the user's tire size to calculate all of the other statistics that are then finally displayed on the phone screen. The device is also rechargeable via USB power. So now that we have described the system functionality, we will have a live demonstration of the system operating normally. Okay, so this is the live demonstration of the Bluetooth bicycle sensor. So right here we have the central module, which contains the microcontroller and the battery and charging circuit, as well as the battery itself. And here you can see there's a USB charging port as well. And attached to all of this is our sensor, which is a reed switch, as stated before. So now we'll show how it is actually installed on the module, and Michael will describe it as I do it.
Alright, so if you can come in closer here, we've got the magnet right here taped to one of the spokes. And so every time the wheel makes 1 rotation, it'll activate our magnetic sensor right there. And so every time it activates the sensor, it'll send the signal all the way over to our module, which will rest right underneath the rider. And so when the module receives this signal, it'll send it over Bluetooth low energy over to our phone. And the phone will update based on the speed that the wheel is spinning at. And so we'll show you the app now and how it works. We'll spin the wheel and show you how everything comes together.
So if you want to come in here, so I'll open the application and it asks me to turn on Bluetooth, which I'll do now. And there's our module right there on the list. So I'll open it and it's now connected. So now Michael will lift the wheel and simulate some motion.
It's not showing.
And there we go,
Oh,
starting to show. And as you can see, there's trip time, distance traveled, average speed, average RPM, current speed, current RPM. And you can see I can switch to empirical units if I want. So now it's in miles per hour and miles per hour here, as well as miles for distance traveled. And I can also switch back, obviously, back to kilometers. I'm also able to modify the tire size in case I'm using a different bicycle. So I can say my tire size is 2.06 meters instead.
Let's make that clear. Okay.
And so now it's set to 2.06 meters. You won't be able to see that very easily unless you ride for a long time, obviously. And then I can also just reset the data in case I'm starting a new trip. Real quick, there we go.
It's new.
And distance traveled is now back to 0.
And we can also show that how it would work for a normal student by mounting this on there. And so it's just as easy as that. The phone comes off.
Right. So this is how it would normally work. Okay.
So that is our entire system.
Thank you.
Now that we have described the system and demonstrated how it works, we will give a brief overview of how the design has changed over the past 8 months. Because our primary stakeholder and had only a few requirements for us, the design was very open for us. However, because bicycle computers are direct competitors for our system, we decided that we should try our hardest to make the system competitive with similar devices on the market, meaning we wanted to make it as inexpensive, compact, and accurate as possible.
So now we'll talk about some of the initial design. So as you can see, here is our initial block diagram. Is very similar to the system described earlier, only the primary difference being the speed sensor. The initial design, we decided to use an accelerometer to calculate speed. We plan to send acceleration values to the phone and use the integral of the acceleration to calculate the speed. And then the speed could then be used to calculate the distance traveled using the update frequency combined with the current speed. However, using the accelerometer presented a couple of issues. First, BLE only supports transmission of one characteristic at a time, and transmission of accelerometer data would require multiple packets to transmit all the required data. Unfortunately, when we found this out, we were far too along the development process to switch to a different microcontroller that would allow us to use normal Bluetooth. So we had our other sensor working, and building a new Bluetooth interface from the ground up was just not something that we could do with the time we had remaining.
So now that we have introduced this problem, our solution was to remove the speed sensor entirely and use a timer on the app and with the tire size to calculate the speed. So what we will do now is we'll cross out the speed sensor, and after consulting our stakeholder and receiving approval, we were able to make some changes to the app to compensate for this hardware change. What we were left with was our current and final system design.
And so now we'll walk through our final block diagram. As the user pedals, the magnet passes by the reed switch, which sends signal to the microcontroller. This signal then sent to a phone over Bluetooth. This signal is compared to the time elapsed since the last trigger, and this time the wheel circumference is all the information we needed to calculate current and average speed, current and average RPM, and distance traveled.
So now that we've walked through the system, I'll talk about some of the achievements. So one of the things that we're proudest of is our system battery life. So one of our project requirements was that the battery life must be at least 5 days on a single full charge, but due to our design choices using BLE rather than Bluetooth as an interface and a low power reed switch, we were able to get our system to last quite a bit longer than that on a single charge. Although we were not able to extensively test this due to time constraints, we were able to see that our battery was able to last at least 2 weeks on multiple occasions. Another thing that we are very proud of is our Bluetooth Low Energy interface that we developed. The Bluetooth component of the system was by far the most difficult part of the system to develop, especially because none of us were particularly familiar with Bluetooth development before starting this project. And then finally, we are also happy that we were able to develop a very ergonomic system, meaning our module is easy to install and use. People who we showed our system to were very impressed with just how intuitive our design was.
So that said, one of the most important lessons that we learned is to know how interfaces work and their limitation before deciding to put them in the design. If we had searched for BLE, Bluetooth Low Energy, more thoroughly, we would have learned that BLE can only support the transmission of one characteristic at a time, and that the packet size is much smaller, and we would have been able to achieve this, to do this complex job, and with more statistics. Another important lesson we learned is that picking devices with good support is important as developers, we struggled working with our microcontroller because online resources for it were very limited. So we had picked a microcontroller. We would have picked a microcontroller with more resources. Developing our Bluetooth interfaces could have been much easier if we have done that.
And so now that we've talked about all of that, overall we are satisfied with our final product. Despite some necessary system level changes due to some oversight, our system works as intended and it is inexpensive, small, and easy to use. We would like to thank our primary stakeholder, Dewey Nguyen, for helping us develop this project. Thank you for watching.